take the start. All right, welcome back, everyone. Hope you had a pleasant lunch break, and I'm very excited to give the control over to João to tell us about stellar activity with ESPRESSO. Go ahead.
Thanks. Hello, everyone. Welcome back from lunch. My name is João, for those who don't know me. I would like to start by thanking all the organizers of this excellent workshop. I think I've learned so much before giving my talk, and I think I will learn as much just tomorrow. And I'm very happy to be here today telling you a little bit about what we've been doing with ESPRESSO, the new spectrograph, not relatively new, not as new as anymore, on the VLT. So I thought I would go quickly over 4 main points, maybe adding a 5th point at the end. But I really wanted that this 5th point brings up some discussion, and so I think I will leave a lot of time for discussion and for your suggestions on how to best use ESPRESSO data, because I think the instrument is providing very good data and should take advantage of it. So I'll go over ESPRESSO, how it works, basically, how we've been trying to get more precise radial velocities with the new implementation of template matching, and our admittedly very simple model for stellar activity so far, and a few of the planets or candidate planets that we have so far found evidence for. So Suzanne showed the plot sort of like this at the start, less up to date at that time, but you all see here that as we keep discovering planets, we have sort of hit a small barrier in this case at around 1 Earth mass or something like that, and so we are still, as we go forward, I think we want to keep this downward trend, at least maybe not so much in mass, but at least in semi-amplitude. We would definitely like to keep going down in our sensitivity for low mass planets. I've actually plotted here. So this is data from the NASA Exoplanet Archive, and I plotted what they call the controversial planets. I'm not exactly sure what that is, but I was interested if they would be the lowest amplitudes one, but they are not. I guess they have different characteristics. So in this path, I think that's the goal of ESPRESSO, is to keep moving us down this area here as we go forward. And I don't think I need to convince you why we want to find planets, but if I do, that's because maybe some of those will have some sort of conditions for habitability and some sort of future for our species or something like that. And so we are.
You wrong, still won't work.
You'll notice that I am equating Wi-Fi to intelligent life. Let's see. But the goal is exactly this: is to find Earth mass planets, maybe around other stars, which will be maybe slightly redder than the Sun. So ESPRESSO and this path towards it. Let me just talk to you briefly about ESPRESSO itself, the instrument. You see here sort of a drawing of what ESPRESSO is doing. It's an instrument that is designed completely towards high precision spectroscopy and ultra high precision radial velocities with extreme spectral fidelity, and the instrument is aiming towards both studying exoplanets and also studying cosmology, so fundamental cosmology. ESPRESSO can observe, as you see here, this is a concept, but you can observe actually with the 4 UTs of the 4 unit telescopes of the VLT combined, and in that case, it's basically equivalent to a 16-meter telescope. But we typically, for the exoplanet use case, we typically just use 1 UT at a time. But even in that case, it's either one of the 4 UTs that ESPRESSO can use. So there is a
line of fiber. Is it a fiber?
Yeah, there's 4 fibers.
It's fibers.
No, it's not fibers.
Sidereostats?
No, yeah, it's tunnels with just milk, basically.
I see.
And this
Yeah, and there's a fiber.
line and everything, but yeah, otherwise you lose too much fibers.
I see. It's too far.
Yeah, so there is a fiber right at the end, and then but before that there is a coup de train, which is this set of tunnels where light goes through to go from the telescopes into this coup de lab, and pressing the wrong button. Sorry. There we go. And yeah, once it actually gets to the telescope, to the spectrograph, the light is dispersed, and we have 2 cameras, 2 different detectors in the red and in the blue that image the spectra. At the end, there is a pupil slicer, and so we get 2 slices of the stellar spectra in the wavelength range from about 380 to 780. At different resolving powers depending on the mode that we use, but typically we use the high resolution mode with a resolution of 140,000 spectral resolution. So this is the sort of the high view of the telescope, of the instrument. Preliminary, or not preliminary, but what can it achieve actually? You see here results from the paper explaining, from Francesco's paper, basically presenting the instrument. You see how the signal to noise behaves for stars of different spectral magnitude, and we are basically photon noise limited up to magnitudes of about 14, right? And then things start to deviate a bit from this expected relation. And for M dwarfs, we are obtaining the target radial velocity precision of about 10 centimeters per second. And also for G and K dwarfs, at high signal to noise, we are a bit above that, but also within specification. And you see here how the photon noise precision behaves with the signal to noise. Then, yeah. So then we wanted to try to go a bit further in getting more precise radial velocity. So we started exploring if we could implement template matching, a simple template matching algorithm for ESPRESSO data. And this is, I think we all know a bit the motivation for using template matching rather than the CCF approach, but even in ESPRESSO, part of the spectra is thrown away with the mask that is used to build the CCF, and so we wanted to take advantage of that additional spectra. So what we do here is something that André kind of tried to explain under 1 minute and very briefly. So I'll try to be a bit more to take a bit more time here. We first compute a tapas or Delphi, basically to get the telluric template. We select the observation from all the spectra that we have. We select the observation with the highest relative humidity, and so in a way to try to be a bit conservative in what the telluric template, what the telluric transmission will be. And then we make a simple cut on these transmitters of the telluric. So we still throw away quite a bit of the spectra at the end, but often not as much as the CCF masks. Then we combine all the spectra that we have into a stellar template, and we shift them so they are in the same reference, and we combine them. We take the median, and then we compare each of the observed spectra with that stellar template. How template matching works, or its simple version. I guess the sort of the new thing, or the thing we thought would bring an advantage here, is that we are simply assuming that there is one single radial velocity that explains all the spectral orders coming from ESPRESSO. And that means that we wrote our model for the difference between individual spectra and template. We wrote it as, it's basically a Gaussian process, but it's a diagonal one. But it has just simply one parameter, which is the radial velocity, and this is for the full spectrum with the calculation, the difference being calculated within each order, but then the one single radial velocity shift defines the model for the full spectrum range. And so that gives us a bit of precision there. And what we do is then we put this model into a Bayesian framework, and we can estimate the posterior distribution for this radial velocity shift, either with a simple but lengthy MCMC, or what we do is we take the Laplace approximation of the posterior, and then we get a best radial velocity and uncertainty. So this happens to work quite well. And so we found that we did a comparison, André showed this very briefly. We did a comparison with all the stars that were observed with ESPRESSO up to a certain point. So there's about 1,000 ESPRESSO spectra in this comparison of 33 stars. And here you see the ratio between the RMS of the DRS radial velocities, so CCF radial velocities, compared to S-bar. Let's just compare this line here. This is our classical template matching, which doesn't have this single radial velocity shift assumption. And you see that for all of the M stars and the K stars, we do slightly better in terms of RMS. We decrease RMS a little bit relative to the DRS. For G-type stars, not as good, but we're doing okay. And then in terms of precision, so here you see the median radial velocity precision, the radial velocity error that we extract from the template matching and from the DRS, and you see that there's a huge improvement, a very large improvement for M-type stars and also K-type stars, up to 50%. So sometimes we see a reduction in the radial velocity error of almost 2 times. So I'll give you here just the example. I'll talk a little bit more about Proxima Centauri a bit later, but this is the result we get for the radial velocities of Proxima Centauri. These are the DRS CCF radial velocities. These are the template matching radial velocities. They're still DRS radial velocities because we use all the outputs from the DRS. It's just we don't use a CCF, we use a template matching approach. And so you see that in terms of RMS, they're very similar, but we get substantially lower uncertainties in the radial velocities. There's Andreas' poster if you're more interested, or talk to him or to me about this. And we are waiting for the referee report on this paper. Then let me talk to you about how we are using these radial velocities to model stellar activity and planets. And here it's the part that I'm slightly ashamed to be presenting you such a simple Gaussian process in the middle of all these complicated ones. But all we have been doing so far, or most of what we have been doing so far, is assuming that we are modeling the radial velocities and the full F maximum with a common Gaussian process. Okay, that's common in the sense that it shares hyperparameters, and mostly using the typical quasi-periodic kernel that we have heard about. I was giving a talk about this model, and I got a question from the general public audience that are you just using simple statistics to find these planets, or are you using any machine learning? And I had to say simple statistics, but I still think, yeah, they are simple.
Technically, I think Gaussian processes are considered part of machine learning, so you can say yes.
Yeah.
Easier machine learning.
I mean,
But are they simple? Or?
just a quick comment. Question. You said that they were sharing the same hyperparameters.
Yep.
It's only the hyperparameters, or it's the same covariance?
No, so the same.
The hyperparameters define the covariance,
Yes, they share the same kernel.
but they don't share the same function.
But yeah, in this sense, they
Yeah.
don't share the same function in this case.
Yeah.
Okay.
I did relax this assumption. Sometimes we relax this assumption in terms of which parameters, which hyperparameters they share. And that sometimes can lead to different results.
But if you
As
don't
we-
share the same function, you have to worry about overfitting.
Yeah.
I
agree.
have a question. I'm sorry. Maybe we should keep it at the end, but I was worried we were going to move completely off topic. But on the template matching, there was something written on your slide that you did not say aloud, but that intrigued me. And it was about, you said the continuum is marginalized out.
Yeah, so in order to compare each individual spectra or each order of the individual
Yeah.
spectra to the template, we divide them
Yeah.
and then we fit a slope
Yeah.
to that division. And the parameters of that slope are analytically marginalized out.
Okay.
So are just those two parameters
So
of
it's
a
a
linear slope.
linear.
Yeah.
thing.
Or it can be, we can use the quadratic, a more complicated thing, but they are marginalized out. And so we simply have one parameter in the whole model.
Mm.
Okay, so that's a simple Gaussian process model. I will talk very briefly because I think it came up in the discussion, and it's something that we've been working on for a while. But it's an aside because I haven't tried it on ESPRESSO data yet. We have been working on something called Gaussian process regression networks, which is an idea that I think came up somehow, which is to just throw more GPs at it and in this case multiply different GPs one with another. And so here you see the basic idea. We have sort of an input quantity, and then we have nodes, a number of nodes, and weights, which themselves are, both of these are GPs, okay, and they can have different covariances, different parameters, or they can be shared as well. And then the linear combination of these nodes and these weights provides or tries to model each of the activity indicators and the rate of velocities at the same time. So we've had a bit of success with this model when applied to ARPS north-south data. You see here, we are using a simplified version of this regression network here with just one node, a quasi-periodic kernel with a quasi-periodic kernel and two weights with a squared exponential. And you see here how it models the rate of velocities and the full if-off maximum of the ARPS, of the full ARPS north, the 3 years of data. The advantage of this network here is that it provides non-stationary outputs, and so the outputs that we are using to model each of the time series are not Gaussian processes. But they are non-stationary because of the multiplication of the GPs. It is a bit harder to learn. It's been challenging to do inference on this model, and I think we are clearly missing nodes and freedom here. But still, we are able to reduce the RMS of the ARPS north-south data quite by a bit. Thank you. But so that's an aside because we are working on the application to ESPRESSO, and that's not yet done. Then let me go through the low mass planets or planet candidates that we have detected around nearby M dwarfs. I'll start with this result that you saw, I think, in the presentation of WARS yesterday. That is the case of L98-59. This is part of the ESPRESSO programs that are searching for planets and confirming transiting planets. In this case, we have 3 known transits with test data, and there is a detection, and we detected with ESPRESSO data 4 planets, so the 3 transiting planets, a 4th one, and a 5th candidate that could be inside the habitable zone of this star. And you see here how the model how we had to model stellar activity for this data, but you see also, as Lars pointed out, the comparison between what HARPS was giving us and what ESPRESSO is providing. Then, in this particular case, 2 of the planets are have a similar internal composition, and then there's planet D, which could have a significant amount of water. So ESPRESSO and these sort of activity models are being used to confirm transiting planets. Then there is just a second case of Proxima Centauri, which we have observed Proxima with ESPRESSO quite intensively over the last few years. Initially, what we did, we published a paper led by Alejandro at the time that we were able to confirm the presence of Proxima b, so the planet at 11 days. I just decided to show you here a result from that paper, which is the correlation between the activity signal in the radial velocities and the activity signal in the full width-half maximum, which shows this lack of correlation, this circular behavior. But then when you take the derivative of the full width-half maximum, the correlation is much more clear. And so this points in the same direction that we've been discussing for the last 2 days, that there is a component that is the F prime component. Then we kept looking at Proxima. So it did change here.
It sometimes can take a little bit of time to update.
Okay.
There we go.
Okay. Yeah. So we kept observing. We kept observing Proxima. This is the initial data that we used back in 2020. We got another campaign to try to confirm, because in that initial paper we found the first hints of a signal at 5 days with a very small amplitude, and so we got extra data to confirm it. You see here the radial velocities and the full width-half maximum divided in 3 chunks, because as other instruments, ESPRESSO is also not free of interventions, and we keep trying to improve it. And so we have to assume that some of those improvements may lead to offsets, radial velocity offsets, and so we wanted to separate and to model those offsets. But here the average, the mean error bar on the radial velocity, we're talking about 30 centimeters per second. Then with this data, if we model this data with that simple shared Gaussian process model that I showed you, what we detect is 2 very clear signals, both in the CCF radial velocities and in the template matching radial velocities. And you see here how the evidence for the 2-planet model has been increasing with increasing number of points, and also how the posteriors for the period and the semi-amplitudes have been getting defined as we observe, as we get more data. Going quickly through this, if the slide moves. Sorry, it's moved there. Okay, there we go. There's the constraints on the Gaussian process hyperparameters, which are, I forgot to say, I'm not sure I said it. So these hyperparameters are shared. The amplitudes of the Gaussian process kernel are not shared, because they have different amplitudes, the RVs and the indicator. Okay, so what you see here is the final, the best fit model. You will see here at some point. That's okay. There we go. So you see, I think it's funny to see that the Gaussian process model, so the stellar activity model, you can already see by eye the shifts that we've heard about, right? And so the peaks are offset and are lagged between the indicators. And then you see the residual RMS is that we get at the end with the two-planet model is comparable to the photon noise uncertainties. Here's the constraints on the two planet candidates. So there's Proxima B. There is there. One. You have to. I'm sorry.
It's fine. It's a nice plot to look at it.
Just keep looking at this one.
In the top row, what's the black line versus the pink line in the top row?
So the pink one is just the Gaussian process component.
Yeah.
And the other one is plus the two-planet model.
Got it.
So it's the full model. I'm really sorry, but this. Should
There's
I
some
do anything?
really interesting structure in the residuals.
There is, yes. I agree. And part of the interesting structure is that it's much lower in the ESPRESSO 19 data set than in the other two. And we are not 100% sure why that is happening. But the sampling in this data set, in this subset, is also slightly different. And okay, there we go. So here I'm just showing you the phase curves of the two-planet model with the ESPRESSO data from the different chunks. So let me go through this.
What network are you on?
I'm sorry,
What network are you on? I'm wondering.
the OWL.
Sorry.
Or is it my computer?
Your computer, because your computer's okay. It's the connection between your computer
Okay.
and Teams.
It just changed.
Which one? Okay, I can show you this one, I guess. So this is it's the confusogram that I will try to quickly through. It's just to, I think this is showing you the predictive mean of the Gaussian process for both the radial velocities and the full EFF maxima. And the color here represents just the time. And the point here is to show you that the peaks, both in the radial velocities and in the full EFF maximum, are changing over length scales over time scales of 1 or 2 rotation periods, or up to 3 rotation periods. And so this could be a hint if this activity signal is being caused by the same active regions within the star. We think this can be a hint of differential rotation as the active regions change latitude. But it's not clear if this assumption is.
Can't it just be growth or decay?
Also. No, it can also be. Yeah,
You
but
can use that. You can't distinguish the two.
you cannot distinguish. No, if they are the same active regions with the same size, I think it would necessarily be differential rotation, but it can also be changing size.
If the size doesn't change.
Yep, I agree. Okay. There we go. So just to tell you that with ESPRESSO, we are starting to peer into this part of the parameter space of low amplitude and low mass exoplanets, and that's where we're headed with this instrument. And then just to finish, I will try to show you my conclusions, and then very quickly I will mention this project that we have been thinking about and we have been trying to put into practice, which is to, guess what, observe even closer stars than Proxima and actually point ESPRESSO to the sun. And in this case, with POET, with the Parallel Solar ESPRESSO telescope, what we are trying to do is not only to get sun as a star observations, but also to actually resolve the surface of the sun. So in terms of spectra with ESPRESSO, in terms of time with continuous observations, and in terms of space with different fibers fixed on different active regions within the sun. And so we think that this might help in the future to let us understand the building blocks of the signals that we are obtaining in the radial velocity. If we look at the small constituents, the small parts that make up those signals. So I think I will stop here. I did not leave much time, I'm sorry, but that's it. Thank you.
Excellent talk. I'm afraid we don't have time for questions. I know everyone's very excited. We saw it during the talk. I do recommend to everyone just post the questions in Slack and we can answer it. But in order to keep on schedule, I think we do need to move on. And if Marina could share